Okay. Good. Starting now. Good morning, everyone. Today we are going under the hood of AMD Ryzen 5 9600 to look at its cache architecture. This chip is based on the new Zen 5 Granite Ridge design. As we go through these slides, I want you to keep one thing in mind. In modern computing, we aren't actually limited by how fast we can compute anymore, but we are limited by how fast we can move the data into the core. Let me introduce myself. My name is Imanisri Ajay Karthik. My roll number is 230102030, and we are group 14. Moving into the contents. These are the contents of the flow. These will be the contents of the flow. Going to the next slide. Now the 9600X is a 6-core, 4 nanometer beast with a 12 thread with 12 threads. The big headline for the Zen 5 is the massive structural widening. It introduced a native 512-bit data paths for the AVX 512 instructions. Think about like this: the CPU can now process twice as much data per cycle as the previous generation. But that creates a massive design philosophy challenge. If you don't re-engineering the memory subsystem to feed those wider pipes, those executional units are just going to sit idle. The memory wall. So why is it so hard? Let's look at the numbers. At 5.4 gigahertz, a single CPU cycle is less than zero point 0.2 nanoseconds, but a trip to DDR5 RAM takes over 100 nanoseconds. That's a 540 cycle penalty. If the CPU misses its cache, it isn't slowing down. It isn't slowing down. It's effectively standing still for over the next 500 cycles. While the memory bus catches up, the cache job isn't just storage. It's an insurance policy against a catastrophic latency gap. We'll go to the reorder buffer. So now the CPU tries to hide this with the out of order execution using a reorder buffer. But Zen 5 is a 8 wide reorder buffer, meaning it tries to retire 8 instructions every single cycle. So here's the math. If a memory stall lasts around 540 cycles and you are doing 8 instructions per cycle, and you would need a raw reorder buffer of size 4300 entries to stay busy. But no modern processor today has that big buffer. Eventually, the ROB overflows, and you will hit a hard stall where the entire core just freezes, not utilizing our 512-bit pipeline. So, in order to solve this, we have the AMD Zen 5 uses a three-tier cache hierarchy to stop these stalls. L1 is a volatile frontline, extremely fast at 4 cycles. L2 is 1 MB private staging, also called staging node, and L3 is the shared 32 MB safety net shared across all the 6 cores. As we go down the pyramid, the speed drops, but the capacity grows to catch those misses. L1 has a split cache system, whereas instruction set has 32 KB and the data caches has 48 KB. Moving to the next one. The L1 data cache specs. The L1 data has been beefed up from 48 KB and 12-way set SOSVD from 32 KB to and 8-way set SOSVD. Why? By giving the memory addresses 12 possible slots to live in, we drastically reduce the conflict misses. It's a space for a performance trade-off. More slots mean fewer evictions during heavy workloads. And also the structural layout will be the cache is divided into 64 sets utilizing the standard 64-byte cache lines. The L1 instruction cache. Interestingly, the L1 instruction stayed at the 32 KB as Zen 4. AMD strategically prioritized silicon area for widening of level O op cache. Instead, it's more efficient to store already decoded micro ops than to keep the redecoded one from a massive L1 instruction set every time. Port asymmetry. This is a key architectural trade-off to feed those 512-bit vectors. The L1D has two 256-bit read ports and one 256 write port. Why the asymmetry? Because the code statistically performs way more loads than stores. Two read ports allow a full 512-bit load in just one cycle, but a 512-bit store mathematically cannot fit through the single 256-bit port in one go. So it takes 2 cycles. It's a calculated sacrifice to save physical silicon space while keeping the most common operations fast. The eviction bus bottleneck. So we also have a physical dimensional mismatch. Cache lines are 64 bytes, but the internal bus to L2 is only 32 bytes wide. So you physically cannot push a 64 byte block through the 32 byte pipeline in one cycle. This is this is why transfer in each step is a 2-bit process, taking 2 consecutive cycles to move one full block. TLP and VAPD. So how do we find data in just 4 cycles? This is where VAPD comes in. Programs use virtual addresses, but hardware needs physical addresses. If we waited for the TLB to translate the address before checking the cache, we would be too slow. We cannot achieve our 4 cycles latency. Instead, Zen 5 uses a look-ahead strategy. It sends the lower bits of the cache rows into the backup to wake them up immediately, while simultaneously sending the upper bits to the TLB. It's a race. By the time the cache data is ready, the physical tag is there already there for near instant hardware comparison. So the VIPT has a mechanical advantage. Simultaneously, since we will be doing lower 12 bits of the index into the cache rows, while upper bits are sent to the TLP, they are being done simultaneously and parallelly. And also the race to the compare. The SM array discharges and reads the 12 ways at the same exact time. That TLP provides a physical tag. Now we'll come across aliasing fix. But VIPT has a danger thing called aliasing, where two virtual address point to the same physical data, but end up in two different cache sets, leading to corruption. AMD solved this with pure math. Aliasing is impossible if the base size is less than or equal to the OS page size, which is the OS page size typically is around 4K. So AMD chose 48 KB capacity as a cache capacity, as a cache data capacity, which is 12 ways. So when you divide it 48 KB by 12, it's exactly 4 KB per way. So this perfect match, the index bits are guaranteed to be identical, defeating the aliasing through dimensional design. The L2 coming to the L2 cache. L2 specifications. L2 is 1 MB private unified pool because it has more relaxed latency of 14 cycles. It doesn't need the race of VIPT. It uses PIPT, physical index, physical tag. It waits for the full translation because it has time, making it completely immune to the virtual memory implications. Moving on to the wave prediction. Searching 12 ways every cycle is a power disaster. Zenfire uses wave predictor, a speculative hidden table. It guesses which way holds your data. If it is right, we get minimal latency and 80% of the power is saved. If it misses, we only lose one or two cycles to a standard. We only lose one or two cycles to do a standard search. It's a guess before check logic that keeps the chip efficient. Moving to MSHR and non-blocking cache. Zen5 is non-blocking. When a miss occurs, the miss status holding register MSHR acts as a waiting room. This allows the CPU to perform hit under miss. It keeps processing instructions that result in the hits, while MSHR handles that 2-bit transfer from the L2 in the background.
పోయింది. So, hello everyone, I'm Venkat Saiteja. So, now I'm going to say about how the data is moved across the caches and how the misses are handled and everything. Handling of miss is very important as the average memory access time depends on both miss rate and miss penalty. So, when we think about the misses, there are majorly three kind of misses. One is the main one is the compulsory miss, which is almost unavoidable. Compulsory miss happens when the processor requests a block of data for the first time. As it was being requested for the first time, it has to be retrieved from the main memory or maybe some other hierarchy of the cache. So it is most like it will be a guaranteed miss. One of the way to improve this is by hardware prefetching. We'll go to that in the next slide. And the next kind of major miss is the capacity miss. The size of the cache is small, so it can't hold the entire data required for a program. So when the program is running, when the cache becomes full, so when the new block is requested, so there must be some eviction of the already existing block. This is the limitation caused by the size of the cache. To improve this, we can do by increasing the size of cache, but there is a trade-off for it. Increasing the size of the cache will result in increasing the miss penalty, which further increases the memory access time. So we have to go through this trade-off. The other most commonly occurring miss is the conflict miss. This miss happens when two blocks of data are mapped to the same set. So when they are reoccurring, like let's say in a loop, when both of them are when processor requests both of them, so they will mutually mutually evict each other. This causes continuous conflict misses and will increase the miss rate a lot. So one of the easiest and mostly used way to fix this is the increasing set associativity. That's what many processors do. Uh, Next, as we one of the major way to improve the overall memory access time is doing hardware prefetching. The main idea of hardware prefetching is that we'll bring the part of a block of data by assuming that it may be demanded in the future. Not it will be demanded. The data might not be adjacent, or it can be some different data than the current running data. Uh, our processor has three main methodologies of executing this hardware prefetching. The first one is stream prefetcher. The stream prefetcher is used to identify sequential access pattern. Let's say in case of arrays, the data is most likely being accessed in the future. So we'll bring the subsequent elements of the array before they are demanded. Other methodology is region prefetcher. This completely the main idea of this is using the advantage of spatial locality. If one piece of data is touched now, there's a high chance that the surrounding data might be accessed in the future. And next methodology is straight prefetcher. This is one of the unique prefetcher in this 9600X processor. So basically, it is good in doing two-dimensional memory jumps. So it was very efficient in the matrix calculations. So very useful in AI model trainings and where heavy matrix multiplications are required. So moving on to the next one. Uh, as the cache size is limited, also the bus size. So whenever a block eviction happens, I mean, when the block is being bringed from one hierarchy to another hierarchy, we can't transfer the entire block at a time. So we go by ward. The critical ward first policy is about bringing the demanded, the most required word beforehand, before all other words. So the required log directly goes to the execution unit, while in the background, remaining words are being transferred to the L1 cache. Next, based on when we go to writes, based on write hits, there are two policies. If there is a write hit, the two policies are write true and write back. This processor uses write back. Write true is basically when there is a write hit, it will update both L1 cache and the main memory. In case of write back, it will only update the L1 cache, but the main memory is updated when the 30 bit is shifted to 1. It is going to be evicted. Like the next policy is write allocation policy. This happens when the write misses happen. So right, there is two kind of these policies: write allocation policy and no write allocation policy. Write allocation policy is that uh, cache goes the main memory fetches the entire block into the L1 first, and it is updated there, not the main memory every time. Next, coming to the major part now, block replacement policies. The reason for block replacement policies, again, the size of the cache is limited. So when all the blocks are filled in the cache, we need to evict some block. There are very many different strategies to do this, and one of the famous one is least recently used. It is in hope that the least recently used block is not accessed immediately in the future. But this is a very excellent strategy for small set associativity. But when we take a processor like us with high associativity, like 12, the LRU implementation is basically storing the chronological order of recent references to each blocks. So it basically implementation is with a linked list. So when every time we modify this entire linked list, it will take a lot of time, mostly often time. So to fix this, the 9600X processor use pseudo LRU. Pseudo LRU is not a true pseudo LRU algorithm. This tree based is a practical solution for pseudo LRU problem. Here we encode the referencing order using a binary tree, and uh, the access time here is just O of log n, which is a huge improvement from O of n. If we take an example, let's say take a 8-way set associated to cache, and the working of it is basically the when the let's say in this example the j is referenced, so the part is the upward from the root node to the child node, from the child to their child node, finally it is accessed. So here the LRU part is opposite to this. In the first case, the reference is upward, so the LRU will be in the downward direction. Similar way. Based on this, after all continuation of all the process, when finally all the references are done, if we trace all the pointers back from the root node to the final block, that block gives us the pseudo LRU block. So basically, in this case, the B block is pseudo LRU and A block is most recently used block. So here we try to evict the B block. Also, if we take kind of bit about the number of bits used for all the here are like if there is a if this is a 8-way set associated to cache. In the binary tree, we are using 7 bits to represent the pseudo LRU order. So the overhead is here 7 bits for all the 8 blocks. So if there are 8 block a number of blocks, we require a minus 1 number of bits for storing encoding the partial order. So the overhead is a minus 1 by a bits per block. So coming to like the purpose of this block replacement policy is to find the block which have to be replaced. Next, how this is replaced. Like before replacing it, we'll check the data bit. Like if data bit is 1, it means it, the data in main memory and the cache is different. It is modified. So first we need to update the data in the main memory or some hierarchy in the lower caches, then evict the block. If the data bit is 0, we can directly, it means the memory and the cache have same content, so we can directly evict the this block and add a new block. So these are some of the ways to improve the overall average memory access time. So my friend will continue from here.
Hello, my name is Dhruv Kondapi and I'm going to take over from here. Moving on to shared hierarchy, the L3 cache act as a core complex thinker with 32 megabytes of capacity. Unlike L1 and L2, it is a shared equally among all six cores, providing a consistent 40 to 50 cycle latency. It is 16 set associative divided into six slices. Non-intrusive victim caching. Let's look at how data enters L3. First, note that a fully associated 64-bit victim buffer sits between L1 data and L2 caches to catch recently evicted data. The massive L3 itself acts as a macro scale victim pool because Zen5 is strictly non-inclusive. Data fetched from DRAM directly goes to L1 and L2, bypassing L3. L3 only catches dirty data that gets evicted from when code's private L2 fills up. Cache coherence problem. Since L3 is shared, we hit a major hurdle, cache coherence. If multiple cores hold and independently modify the exact same data in their private caches, this risks silent data corruption. To fix this, architects generally use two solutions. Write update. Write update forces cores to constantly broadcast new data across the bus. Write invalidate simply broadcast a message telling other cores to trash their outdated copies. The 9600X uses more bandwidth efficient write invalidate approach. Snooping protocols. The invalidation is managed by a snooping cache coherence protocols. Essentially, all caches continuously monitor or snoop the shared data bus for these broadcast invalidation messages so that they know when to drop the state. Specifically, uh, AMD utilizes MOSI protocol. This stands for Modified Owner Exclusive Shared Invalid. Each state dictates exactly what operation a core can perform on a cache block. Let us move to the most biggest flaw of messes. Imagine core 1 has a variable in M state and core 2 wants to read it. Under standard Messi, core 1 cannot simply share the data. It has to force a stall and write the data all the way to the main memory, and only then the core can share it. Similar write back happens when on a write miss. Memory write back is a massive latency bottleneck. This is fixed by the owner state. Now let's see what happens. On a read miss, the block must be in MOE or E state. The cache confirms it has the correct local value and simply returns to the CPU with no state change required. On a write hit, uh, if the core state is in S, it moves to M, and all other cores with owner state will move to invalid. Since since the core sends out intent to modify signal across the bus, all other states having that data will invalidate their copy, and the one which writes the latest value claims the state M. The role of the owner core becomes solely responsible for that dirty block. If another core wants to write, the owner transfers the data and invalidates all other copies. We only write to main memory when the owner finally evicts the block due to capacity limits, freeing up massive amounts of memory bus bandwidth. Pitfalls and solutions. There are two physical pitfalls programmers must watch for. Cache ping pong happens when core constantly overrides the same variable, triggering endless fetch and invalidate cycles. And second one is false sharing. Occurs when independent variables across the same 64-byte cache line causing accidental invalidations. The software fixes memory padding to separate the variables. Op cache and branch target buffer. Finally, to keep the execution engines fed, the system uses a level 0 op cache. The high-speed SRAM buffer stores pre-decoded micro operations, completely bypassing the heavy instructions decoders. Alongside this, The branch target buffer caches the exact destination of the addresses of previous branches, preventing catastrophic pipeline flushes. Conclusion. In conclusion, the Z5 cache hierarchy is a masterclass in logistics, from geometric VIPT routing to defeating aliases and to tree PLRU evictions and to bandwidth saving MOSI protocol, even transistor to design, maintain strict data integrity and keep the reorder buffer fed. Thank you.